So, Antonio, I will just have a very short introduction. So you received the PhD degree of University of Napoli, Federico in 2007, and then now you are a research director of the Italian National Research Council in Naples, Italy, and you are a well-known expert of differential interferometric SAR. You have been visiting professor in many places, but I will not give too many details about that. So I will just give you the floor, and we are very happy to listen to your talk.
Thank you so much. Sorry for the problems that we had. So this talk is about a short presentation about the multi-platform interferometric SAR approaches for the generation of three-dimensional ground displacements products. So mean deformation velocity map, deformation time series, and so on. The presentation is made by several steps. First, I tried to very shortly introduce the principle of ground instability analysis with InSAR. Then I will be more focused on the generation of three-dimensional maps. When I see three-dimensional, I consider that deformation is originally in the three-dimensional space domain. So we have deformation along the up-down direction, the east-west direction, north-south direction. As we know, the InSAR analysis based on one single orbit is not able to reconstruct the component of the deformation along north-south, but using different flight orbits or even using ground-based SAR instruments, we are able to reconstruct the 3D domain. Then I will spend a couple of minutes regarding the analysis of burst overlapping interferometry, which is a relatively new approach to reconstruct the north-south components. And finally, if I have time, I will introduce some other research and products. I'll try to use directly the papers we have published recently, so interested people can then ask me or search for the relevant papers online and have additional information. So I will try to use equation as not so much. So I will show some equations, but interested people can then read the papers and maybe send me emails to ask clarifications. So, but generally speaking, I hope that most of us knows about the basic principle of interferometric SAR, so InSAR. I will spend very few words about the InSAR geometry. So generally, we have a sensor that flies along an orbit. We have generally two SAR acquisitions in two different times, so T sub 1, T sub 2, and if we suppose that from T sub 1 to T sub 2, the Earth surface, or in general, coherent targets on the ground has moved from the position P sub 1 to P sub 2, the basic principle of the interferometric SAR technique is to reconstruct the line of sight displacements occurred between T sub 1 and T sub 2 by computing the phase difference between the master and the slave image. And very, very simple, the relation that relates the phase difference with the component of deformation along the line of sight depends on the wavelength. I work at IREA CNR in Naples. In IREA, in 2002, the SBAS method was developed. Very shortly, we start from raw data. We focus this data so we have complex SLC images. We co-registered this image and we generate interferograms. The interferograms represents the phase difference between a couple of images. In general, we do not have only one image, two images, but we have lots of images. And so we can generate a series of interferograms. And starting from these interferograms, we are able to compute the line of sight component of the ground deformation, and we can able to reconstruct the ground displacement time series and the mean deformation velocity maps. This is the basic idea of SBAS. Mathematically speaking, this is a very old-fashioned slide. We have several interferograms. From each interferogram, we can build up an equation. So we have a system of linear equation that is solved. These are the known terms, so the computed phase differences, and these are the unknown terms, so the phase associated with the time acquisitions. So we have a system of linear equation. This system is solved, and we can obtain the phase associated with the single images. So we have the deformation time series. Actually, in 2002, my colleagues demonstrated that this solution is not physically reasonable, and so they move from the phase to the velocity. Mathematically speaking, they moved from the phase to the velocity differences, and they obtain another system of linear equation that is solved using the single value decomposition method. Once the velocity v that is represented by these equations is determined, this velocity is integrated in time, and so at the end, the deformation time series are obtained. This is the basic rationale. A first step is to try identifying which are the pixels that have been correctly analyzed, correctly investigated. In 2006, Riccardo Lanari and I developed this, used for the first time this estimator that is known now as temporal coherence. The temporal coherence gives us a measure of the correctness of the solutions that we have obtained, because we estimate with SBAS the phase, so the deformation time series. We compute the difference between the original interferograms and interferograms reconstructed from the deformation time series. So let me say, we reconstruct residues. These residues represent errors. So more errors we have, more likely this estimator tends to be zero. In case that we do not have errors, so the reconstructed interferograms is exactly the same as the original interferogram, we have 1. So it is a sort of probability term. If gamma, so if the temporal coherence is 1 or tends to be 1, it means that no phase unwrapping errors were committed, and the reconstruction of the deformation time series was perfect. In the interferograms, and so the relevant targets, the relevant pixel must be cut. So it is an estimator that can be used, that is used by us, but also by other scientists now, to establish which is the set of good pixels well processed, and which is the set of bad pixels that have been not well processed. And this is the starting point. So what we can do, considering one single orbit, one single set of SAR images. But now, and even more in the future, we will have lots of constellations of satellite, constellation of SAR sensors. So the idea is to move from one single orbit to a constellation of satellite, to a constellations of SAR sensors, so to a set of independent measurements that can be obtained by the different sensors. These sensors can work at different wavelengths, can work at different with different illumination angles, can work with different polarizations and so on. So this represents one of the many research issues developed not only in IREA, but everywhere now. So the multi-viewing geometry, if our goal is to reconstruct the three-dimensional field of deformation, we need to start from this observation. If we have at least two viewing angles, so two viewing observations. So typically, if we have an ascending orbit, an ascending trajectory, and a descending trajectory, and we have a given deformation, this deformation is, of course, has three components. As components along the east-west direction, as a component along the north-south direction, and as a component along the up-down direction. And this picture allows us to decompose the deformation into these two planes. So the first plane is the plane up-down east-west, and the second plane is the plane north-south, and the projection of the 3D orthogonal to the north-south direction. So in general, as we know, flight orbits are almost parallel to the north-south direction. So using only satellite information, so using only satellite SAR sensors that flight along polar orbit trajectory, it's quite impossible to reconstruct the north-south component of deformation because this angle phi is very, very small. So typically what we can say is that this component of deformation is not so important, and so we try to decompose the deformation along the east-west and the up-down. And this is typically done when we work only with satellite data. But in general, we can also integrate complement information from the satellite and from the ground. And so in general, this equation represents the starting point of the following analysis. It is derived from basic trigonometric consideration, basic geometrical considerations. So the idea, already developed more than 10 years ago, was to apply ISPRS, but even also another kind of method, maybe PSI, or another kind of method that allows us to obtain the deformation time series, not only to one InSAR set, but to several datasets. So we have a first SAR dataset, and we have the deformation time series obtained using this first SAR dataset. We have so the line of sight deformation time series, and we have the temporal coherence. Actually, we also have additional information like the residual topography and so on. And this can be done using the first SAR dataset. In general, we have another SAR dataset. We have a third SAR dataset. So in general, we have more SAR datasets. So the idea is the general idea is to combine the line of sight projected ground deformation time series obtained separately from these different SAR datasets in order to estimate the 3D components. As we said before, using only satellite data, the information related to north-south is limited, but actually this black box can also include external data. So maybe GPS data, other kinds of data, maybe data acquired using amplitude information, now also using optical data. This is the general framework. In 2016, we developed this method, and it has been published. It is simply an extension of the ISPRS applied to several datasets. The idea is simple. we have the first data set, so we have the first deformation time series. We have a second data set, so we have another deformation time series. We have several data sets, and for each data set, we have a relevant deformation time series. For instance, in this case, the example is with 3 data sets. We can reconstruct the line of sight projected deformation from set 1, set 2, set 3, but if we combine this information using this mathematical framework, we can recover the relevant components. So the east-west, the up-down, and the north-south deformation components. The mathematical framework is relatively hard, but what I would like to point out is that we add additional information to obtain this decomposition, and the additional information that was added was relevant to the condition that deformation must be with the minimum curvature. So this method was based on selecting a model with the minimum curvature. Other methods now exist with different kinds of models used, but the general framework is something like that. If we neglect for a moment the north-south components of deformation, this boring system of linear equations becomes like that. But finally, we have the east-west deformation component, and we have the up-down deformation components. People more interested in the mathematics behind this can then ask me or maybe send me emails, and I can explain them more in detail the mathematical framework. We have applied this method in the last 10 years over lots of different data sets. And these are some examples. This is one example related to the area of the Piton de la Fournaise. And for instance, this slide shows not comparison, the ground deformation time series for the up-down directions obtained by combining MVSAT descending, MVSAT ascending, and ALOS data. ALOS data are in green, MVSAT descending are in red, MVSAT ascending are in black. So as we can see now, we combined these 3 different data sets and we recovered the up-down deformation and the east-west deformation. In this case, we discarded the north-south components and we focused only on the up-down and east-west. The same was done for other test sites like the area of the Hawaii. This is the up-down and this is the east-west. It was applied to the area of St. Petersburg. Of course, during the last 10 years, some additional improvements have been applied, mostly related to the statistical information, but boring stuffs. The basic stuff is like that. And recently, we have applied the same method, actually a more complicated one in Vietnam to the city of Hanoi. And there are other several applications of this method in the literature. Finally, I would like to point out on the ground displacement time series, and in particular the up-down ground displacement time series of the area of Shanghai, where I spent several months because we have a cooperation, active cooperation with the East China Normal University. There, in this case, it's quite interesting because this area has been reclaimed from the ocean. So 15 years ago, this area was underwater, and it has been reclaimed from the ocean. And so the deformation that we can see here are related to the compaction mechanism of the soil. The same methods can be applied, of course, to earthquakes. I live in the Campiflagre caldera. Now I am in the middle of the Campiflagre caldera, and in this period we have a series of small earthquakes that are shaking us because this is an active volcano, and we are in the middle of a crisis now. And this map represents the east-west and the up-down deformation of the area. So the method is general and can be applied to several contexts. As I said before, of course, not only satellite data can be combined, but in theory also ground-based data. So a further step is to apply the same framework, the same general framework to a hybrid case where we have two or more satellite dataset and one or more ground-based SAR instruments mounted on the ground. In this case, the ground-based SAR can be mounted with relatively, we are free to mount the ground-based instrument where we want. And so we can reconstruct the north-south component of deformation because we can arrange the position of the ground base in such a way to have additional information regarding the north-south component of the deformation. And this was done, essentially. Actually, we did more than that. We also focused on the statistical characterization of the line of sight deformation, but also on the reconstructed 3D ground displacement time series. The set of equations is almost the same. In this case, we considered that the ascending and descending observations and also the ground-based observations were obtained almost at the same time. So we assumed a quasi-synchronous acquisition situation. Of course, it is not a perfect synchronous because in general, ascending and descending datasets are not acquired in all conditions in the same days. But in particular cases, also using Sentinel-1 data, we have datasets where in the same day, maybe in the morning and in the evening, we have an ascending and descending flight passage. So if simultaneously we have a ground-based mounted on the ground and we are able to mount the ground-based instrument in such a way to have also information regarding the north-south component of the deformation, we can reconstruct the 3D field. This is the diagram flow of the method we developed. And these are additional information about the statistical characterization of the interferograms and of the 3D deformation we obtain. I would like only to spend 2 words. Actually, here we have different sources of noise. The first source of noise is related to decorrelation. Then we have a source of noise related to the atmospheric components. Then we have source of noises related to phase unwrapping errors. We developed with my colleagues a method to estimate these, to quantify these different sources of noise and figure it out in this general case, which is the precision of the reconstructed 3D ground displacement time series. I do not want to bother you with boring equations, but actually we have 3 different sources of noises. One source is related to the decorrelation, and we find a way to quantify this source of decorrelation. Another source of noise was related to phasor wrapping errors, and we identified these phasor wrapping errors and quantified these phasor wrapping errors. And also, finally, we quantified the errors introduced by the atmospheric phase screen. This is the location where the method was applied. And these are the maps we obtained. In particular, these are directly the three components of the deformation. So we have the up-down deformation, the east-west deformation, and the north-south deformation. As I said before, we mounted the ground-based instrument in such a way to have more precisions about the north-south. And so most of the information related to north-south was recovered by the ground-based. And the up-down and east-west deformations were mostly, but not only, recovered by satellite data. Of course, there are lots of problems to be solved and to be addressed. For instance, the dimension of the targets, the fact that the illumination angles are different. All these issues represent source of noises that must be taken into account. This is also the map of the errors. As we can see in this case, the north-south deformation is more accurate than the up-down and east-west. And the reason is that we used a ground-based SAR instruments. And so the information related to north-south was more precise. These are time series. Recently, we have been also involved in a European project, in particular the S34I project. In this case, we also complemented the information coming from different satellites. In particular, in this case, the core was to understand the ground displacements associated with a mining region in the Gummern area. This European project ended in June, and during this project, we applied these methods and integrated with other kinds of advanced methods to reconstruct the 2D, 3D displacements of the mining region. And in particular, these are the maps of the mean deformation velocity of the mining region. We investigated, we analyzed during the S34I project. This is also another possible application. So, and the application of InSAR for mining and for the extraction of raw materials. And this is also a field of research and also an economic field where InSAR is currently applied and maybe will be more and more applied in the future. This is also a slide showing a comparison between the products freely available using the Copernicus services and the advanced products we obtained applying our methods. Another topic, and then I'll try to have a conclusion, is the analysis of very big deformations. In case of very large earthquakes, case of very large deformations, InSAR has some problems because the decorrelation noise tends to destroy the information. In this case, we can recover the ground displacements using alternative methods. For instance, we can use the amplitude of SAR images. We can use the optical images, and we can try to integrate this information with the InSAR data. In a range of deformations that are big, but not extremely big, we can also use other kinds of methods that are still derived from interferometry. And one of these methods is the multiple aperture interferometry. The basic idea of multiple aperture interferometry is really, really simple. We have one image. We have the azimuth spectra of this image. We have two images. We have two azimuth spectra. We can, in general, split the azimuth spectrum of the master image in two slices, and we can split the slave spectrum, the slave azimuth spectrum, into two slices. From the different slices, so from the low frequency and from the high frequency, we can derive an interferogram. And then we can compare the interferogram obtained at low frequencies with interferogram obtained at the high frequencies. The difference of the low frequency and high frequency interferogram is another interferogram. And this interferogram contains information regarding the azimuth displacement. So contains information about the north-south displacement. So we can use multiple aperture interferometry to have information concerning the azimuth displacement. So information concerning the north-south displacement. Of course, the precision, but also the accuracy of these methods of the multiple aperture interferometry depends on the bandwidth we have. So larger is the azimuth bandwidth, more precise are the information we can recover. Without going in details on the equations, actually, we have a multiple aperture interferometry phase. That is the difference between the forward and the backward interferograms. So the difference between the low frequency and the highest frequency. And this interferogram is related to the deformation occurring during the azimuth direction. So occurring along the approximately the north-south direction. And this is the noise. So using the multiple aperture interferometry, we can recover delta x. So we can recover the azimuth displacement that is normally not recoverable using simply the InSAR approaches. In literature, we can find lots of papers describing the spectral diversity and the accuracy and precision of the multiple aperture interferometry. In general, we can say that the accuracy, the precision of the azimuth displacement measures depends on the precision of the multiple aperture interferometry phase. And the standard deviation of the multiple aperture interferometry phase depends, in turn, on the coherence of the observed targets. So in case the coherence is quite large, so here, if the coherence is higher than 0.8, 0.9, even also 0.7, we can obtain quite accurate measurements of the azimuth displacement. This is a comparison. This is a graph related to Sentinel-1, and this is a graph related to MVZ-AZAR. So if we can apply multiple aperture interferometry to Sentinel-1, we can see this picture and we can understand which is the region of coherence where the measurements are good enough. A further improvement of the multiple aperture interferometry is represented now by the ESD, so the enhanced spectral diversity that is applied specifically to Sentinel-1. In case of Sentinel-1, we have the TOPS mode. TOPS mode is characterized by a burst acquisition mode. And if we consider two consecutive bursts, burst I and burst I+1, there is an overlap region where we have a difference of the Doppler frequency that is relatively large. And so because this Doppler difference is quite large in this area, but only on this area, so only on the burst overlapped region, we can recover the azimuth displacement, so the north-south displacements, with relatively good precision, with relatively good accuracy. So if we only consider the burst overlapped region, now the literature allows us to obtain the so-called Boy interferograms, so the burst overlapped interferograms. The same basic principle is used also for the co-registration of top-SAR images, but co-registration of top-SAR images is another story. For this talk, the important to know is that we can recover the azimuth displacements. We can recover the north-south ground displacements that typically cannot be recovered using simply InSAR data, conventional InSAR data. This is the idea. If we compare the multiple aperture interferometry and the burst overlapped interferometry, and we consider some mathematical and statistical equations, we can recover a picture like that. So we can see that the burst overlapped interferometry is more precise than the multiple aperture interferometry applied to Sentinel-1. So in theory, we can apply the multiple aperture interferometry to Sentinel-1, and the result is this blue line. And only on the overlapped region, we can apply the burst overlapped interferometry, and the line is the red one. So the burst overlapped interferometry is better than the multiple aperture interferometry, but the deformation measurements are only available on the burst overlapped region between consecutive bursts. So we have the pros and we have the cons. The pros is that the precision is very, very improved, but we have information only on the bursted overlapped region. This is an example of the burst overlapped interferometry applied to the Ridgecrest earthquakes. We made lots of experiments during the recent years, of course, not only in IREA. This is a general topic applied everywhere. Also, Chinese researchers are very interested to this kind of topic. And these are some examples of the Boy interferograms, so the burst overlapped interferograms we recovered for the Galapagos Islands. For instance, this is an interferogram, Boy interferogram related to May 13, July 18 of 2018, in correspondence of a big eruption occurred in the late June of 2018. As we can see, the north-south ground displacement map is very clear. So this is the overlapped region between two consecutive bursts. So we were lucky, and so we can recover here the north-south ground displacement with relatively good precision. But maybe if we want to know which is the north-south displacements here, we can apply other methods, or even we can try to extend this information from the burst overlapped region to the external region. And this is one of the key issues we are working with in this period. The burst overlapped interferometry is a reality. So all of us can apply this method, of course, searching for mechanisms with responsible of big deformations. If we would like to apply this method to small deformation, it is a waste of time, because of course the precision is improved, but it is not comparable to the centimetric, even millimetric precision of the conventional interferometric SAR approaches. These are some comparison of the other, some other informations related to the other components of deformation. So this is the east-west deformation obtained using a conventional InSAR, and this is the up-down ground mean deformation velocity map of the area, also obtained using SBAS. Of course, I work at IREA, so historically I worked a lot with SBAS, but the other people can also work with the PSI, SQUEEZAR, or other methods. The basic principles are the same. We are moving in the same ocean, let me see. Finally, I don't know if I have time for something else.
Maybe you can take 2 minutes so we can keep some time for questions.
Okay, I can only give you some other basic, very, very short ideas on what we also did over the last years. We developed method for the multi-temporal despeckling and noise filtering. This method is similar to SQUEEZAR, similar to the phase triangulation algorithm, but it is only based on the use of small basal interferograms. So with respect to SQUEEZAR or with respect to phase triangulation algorithm, but also with respect to other methods that needs to use all possible interferograms, the method we developed was only based on using small basal interferograms. And so also in this case, we have pros and we have cons. We have also developed other methods, for instance, for the adaptive and statistical multi-scale phasor wrapping of large SWOT interferograms, because now this is also an interesting topic. So more and more in the future, we will have big interferograms, large SWOT interferograms. Maybe we would like to have an interferogram for the entire planet. And so we need to find a way to process these very large SWOT interferograms, trying to make the process robust. So trying to recover the basic information and not spend too much time. Interested people can see these publications. For instance, this is an example of what we did for the area of Italy. This is the Italy, even if it is positioned in the azimuth and range coordinates, so it's complicated to see, but I'm here, the Campi Flegrega there. Another important topic, but I do not have time to go into details, is to understand the inconsistencies of a phase closure, and so to understand the errors due to using very small baseline interferograms in the order of 6 days, 12 days, 18 days. Lots of scholars, and we have also did something, as I've discovered that using very, very small baseline interferograms can introduce additional problems, because a part of deformation can be interpreted as deformation, but it's not deformation. It could be related to other kinds of noise sources, and this is another open topic, very open topic, where lots of scholars are working with. I can share the paper and information to people that who are interested to this method and to the potential applications of these methods to further developments. Thank you so much for your attention. And in case of questions or something else, I'm here, but you can also send me emails or something else during the next days.
Thank you so much, Antonio, for this great presentation. It was very interesting. So we have a few questions. I'm not sure we will have time for all of them, but Okay, well, maybe just the first one. Is it possible for SBAS methods to use input other than unwrapped interferograms? Can you squeeze the unwrapping step, or is it?
Actually, of course, the basic point is to use unwrapped interferograms. I do not. One of the slides that I've shared with you, but it's difficult to explain now in detail. Is related to the development of multi-temporal InSAR methods based on combining information from several sets of equations, so similar to what SQUEEZAR and the phase triangulation does. So SBAS, the basic characteristic of SBAS is the use of small baseline interferograms. So mathematically and speaking, the difference between SBAS, SQUEEZAR, and phase triangulation is that we use only small baseline interferograms. So the method developed by me, Riccardo Lanari, other colleagues now 10 years ago, more than 10 years ago, was based on using only small baseline interferograms to recover the same information that are recovered by SQUEEZAR and the phase triangulation algorithm. Of course, the framework is the same, but the conclusions can be different. Which is the pro in using SBAS and the SBAS derived method? The pro is that you cannot generate very long interferograms full of decorrelation noise, but you can be focused and can be concentrated on using only interferograms that are coherent. This is the basic pro. Of course, in the long interferograms, as we have discovered, there are other information that can be used. So the story is to find a correct balance between using small baseline interferograms with no decorrelation, but also in some cases, long baselines interferograms to avoid the problems related to phase inconsistencies, phase loops, and so on. The topic is very complicated, but the basic difference between SBAS PSI is that we prefer using small baseline interferograms, and SQUEEZAR PSI and the other use long baseline interferograms and are more focused to very, very coherent targets. And it's a very long story.
Yeah, I know. Maybe just another question about when you are combining the different time series that you showed, I think, in the first part. Do you have any normalization process or to safely combine in a non-biased way all the different time series that you have unwrapped independently?
Yes, of course. We started from analyzing the different datasets separately. So for every coherent target that is seen from the different SAR datasets, we know the precision of the line of sight deformation time series. We have the temporal coherence. We have lots of other quality factors that can be used. These quality factors can be put together into the horrible matrix that I've shown to all of you, and the additional information that was introduced in 2016 was about the fact that the deformation is assumed with the minimum acceleration. Other methods are based on constraining the solution to be with the minimum norm. Other solutions, for instance, MSBAS, developed by other scholars, are based on constraining the solution to respect a model. So anyone can introduce a model to try to constrain the solution, because generally we have more unknowns than equations, and so we need to introduce additional information. So if we know that deformation respects a model, we can use this model, and we can put this model as an input of the black box diagram that I've shown to you. If we have GPS measurements, we can use them. If we have pixel offset measurements, we can use them. So it is a general flow
Framework.
where everyone can introduce what he has.
Maybe just another question about, do you think that the extended time annotation product, the ETAD of Sentinel-1, will help to minimize the atmospheric phase screen problem, or do you have any?
Yes, this is another open issue. When I spend a few words about the burst overlapped interferometry, I said that the burst overlapped interferometry, the basic information is related to the north-south ground displacement. This is not true in general. So because the same interferograms also contains information regarding the atmospheric phase screen, also contains information about the co-registration of the top SAR data. So everything depends on how we would like to use the burst overlapped interferometry. So if we use the burst overlapped interferometer first to co-register the SLC images, the core, the basic, the more important source of noise is the co-registration errors. Once we have solved the problems related to the co-registration errors, we will have the north-south displacements, but also in particular conditions, the atmospheric phase screen. And so another story is to separate the atmospheric phase screen in the burst overlapped interferometry from the ground displacement time series. This problem is similar to the problem that we had originally with the SBAS, with PSI, but relatively more complicated because, of course, if we work at L-band, the components related to the atmospheric phase screen can be more significant. If we work at P-band, there's another story. So one of the issues, of course, is to separate the azimuth displacement from the other components. I have assumed in this presentation, this talk, that the more important, the more influent terms were related to ground displacement along the azimuth direction. But of course, you and the other colleagues are right. We can use the same method also to decompose and to extract information from regarding the APS.
Okay. Well, we have many more questions. So maybe what I would suggest is that you can probably interact with Antonio by sending emails. If you
can send emails.
If you have some more technical issues that you would like to, I'm sure Antonio could give you, there are plenty of questions about the way you are combining, taking into account uncertainties and separating the different terms that we are talking about.
Yeah, okay. I understand that the topic is not boring, but it's full of equations. So for me, it was complicated to show something.
But it's a very open and promising subject to combine all sources of information also. So I think that's a great talk for 1 hour. So thanks again, Antonio. And I will give the floor to Lami because she wanted to introduce Professor Derek Lichti to have some communication about the Congress. So like me, I just close from my part.
Thank you so much.
Do I need to stop the?
Maybe.
Can you hear me?
Yes. Maybe Antonio, you can stop sharing the screen. I don't know.
I'm doing that.
Okay. Thanks a lot again. Anyway, Antonio. Thanks.
Thank you so much, Florence, Antonio, and the ISPRS Working Group Technical Commission 3 Working Group 3 for giving us this platform for presentation. I'd like to introduce Professor Dr. Derek Lichti. He's a professor at University of Geomatics Engineering in University of Calgary, and right now he's here to give us presentation as the ISPRS Congress Director. I'm sorry if I introduced you in a wrong way. I just saw your signature in the email and introducing you accordingly. And basically, he's going to present us about different events and activities that are going to take place in Congress. Without spending much time, I would like to hand this platform to you. Over to you, Derek.
Thank you very much, Lakshmi. No, I reacted because I couldn't hear you suddenly. The sound cut out. That's all. Okay, and thank you, Florence, and thank you, Antonio, for a wonderful presentation. It was amazing. I joined late, but it was fantastic to see. And thank you for the opportunity to speak to you today. So I will tell you a bit about the event that I'm organizing, which is ISPRS Congress next year in July, which will be coupled with Canadian Symposium on Remote Sensing, 4th to the 11th of July next year. And I want to give some highlights about that are relevant to the audience here, I hope. And you're, of course, welcome to contact me if you have any questions by email. So to open it up, what I want to do is give you a snapshot of where we're at. We released our big document, second announcement and call for papers earlier this year and open registration on the 25th of August. And we already almost have 500 people registered so far. And that's partly because our very early bird deadline just closed on Monday, but we have a number of sponsors, academic partners, and so forth. So the momentum, I suppose, for the planning of the event is really starting to pick up. And along that line, we have a lot of information here, obviously, but I want to give you an overview of what the program is going to be like, in particular, focusing on plenary sessions. You can see we have so far confirmed 8 very exciting keynote speakers who will alternate from day to day. And these people are from all over the world, from Canada, from the United States, from Asia, from Europe, and we expect them to be a real attraction for the Congress. And ways you can participate are, of course, through submitting your papers and then giving an oral or poster presentation in a number of matters to the in terms of scientific or applied sessions. And there are other ways to participate as well in terms of fora, and there are industry sessions. Well, that's relevant for this audience, maybe. Okay, we also have many tutorials. We actually have 19 of them, 9 full day and 10 half day, if you haven't seen already. We have 9 of those forum sessions. And then in addition to the usual scientific sessions offered by the ISPRS working groups, we have 28 thematic sessions that you can choose from to submit your work. And these are devoted to topics that are not currently covered by ISPRS working groups. And then there are 4 special sessions which are conducted in in cooperation with other societies. And then our symposium has a number of invited sessions as well. On the right are some important deadlines. The main one is when to submit your papers or abstracts for review. And that is coming up in just under 1 month, on the 3rd of November. And then we'll notify you either in mid-December or late January in terms of the outcome of the result of the review results. Okay, we want to have very much a focus on students and young professionals at this Congress, and accordingly, we've involved the Student Consortium in some of the planning already. We've, of course, planned to have a youth forum that will have technical sessions, social events, and networking. And we're in the midst of planning our summer school, which will take place at York University in the north of Toronto. And there'll be days of instruction as well as a sort of design competition. And our intention is that the winner of that competition will be granted some presentation time in the Congress so that people attending can see, oh, these are the scientific leaders of tomorrow. So a bit of exposure for the winners. Okay, you're probably also interested about financial assistance. So I want to tell you about 2 initiatives in particular. One is ISPRS Foundation, which people may be aware of, that provides grant support to attend ISPRS events. We also have Congress assistance grants from a number of different sources, and we've just confirmed a 3rd one as well, so we have additional funds. But the idea here is to provide assistance to students and young professionals from Global South. And these competitions are not yet open. They will be in, I believe it's beginning of December, but just watch our website and all the social media and email activity to find out more details when they become available. These financial assistance measures are more related for people in Canada, but we have additional opportunities from the Canadian Symposium as well as Canadian Space Agency. We've already registered it as an approved event, so the students are eligible for this sort of funding. And you can see deadlines on the right, lots of deadlines there, but December 1st is the day when it opens up competition. Okay, so in terms of accommodation, this is probably of interest to people as well. There are, of course, hotel rooms, but also hotel rooms in Toronto, as well as Airbnb, but we're also working with a number of tertiary education institutions in Toronto, universities and colleges, to provide much more affordable rates for accommodation in Toronto, so you can get to the Congress very easily still too by the transit system we have. Okay, something else that is relevant is the visa application. So we have lots of information. If you come from a country that requires a visa, go to our website, find out all about it. And we have special event registration, so we can get your applications prioritized. We have regular contact with Immigration and Refugees Canada. However, many people do not require a visa. There are many visa-exempt countries and territories, and all that's required is an electronic travel authorization. So go to our website to find out more about that. Okay, so I'll finish it there just by saying that please have a look at our website. If you have questions, then contact me, and I would thank you for your attention. And again, thank you, Lakshmi, everyone, for opportunity to speak today.
Thank you so much. So I think that's the end of the webinar. Florence, do you want to say something and end it? Or, I mean, I can see people are raising the hands. I don't know if it is to ask question to Derek or...
if there's time, sure. Yeah, I can.
I don't know if I can see any questions.
I just allowed. Let's see if they can... they are going to speak. I just see David Brown raising his hand. I unmuted. I'm asking him to unmute, and saw some other people, but now looks like they have put down the hand. Otherwise, maybe, as Derek said, they can email us as well.
Yep.
Email to Derek or the Congress team on the email.
Feel free to send me an email, yeah.
Yeah, over to you, Florence.
Okay, thanks to all the speakers in this case, and okay, see you in ISPRS. Bye.
Bye. Thank you, Derek, for joining at the end, though it was nice.
Yeah, thank you, Lakshmi. I appreciate it.
I'm going